I will chair the last session today. The title of the session is Expressive Synthesis. This is a very popular topic in speech synthesis research nowadays and for some years. And the first talk will be done by Bastian Schnell, improving emotional TTS with an emotion intensity input form from unsupervised extraction. Thank you.
Hello, everyone. Can you hear this?
Share your dark suit in greasy wash water all year.
Did you hear this?
I can hear you, yes.
Okay, perfect. Okay, my name is Bastian Schnell. I'm a PhD student at EDF Research Institute and EPFL. And thank you for your interest in my paper, Improving Emotional TTS with an Emotional Intensity Input from Unsupervised Extraction. So in emotional TTS research, we found that there are basically three ways to go. First way is, for example, you increase the model generalizability by using VAEs or intercross training or domain adversary training, this kind of things, like being smart about the model architecture. Then the second way to go is increasing the data quantity. So you use unlabeled data, for example, audiobooks, or you create artificial data to use that in your TTS system to work out those low amounts of data you have for emotional TTS. And then the third option to go is increasing the data quality, what we wanted to do in this work. So the hypothesis for this work was that the emotions actually localize within utterance. So if you have a single emotion label for the whole utterance, that obfuscates that the emotion intensity is varying. So if we could provide this kind of continuous emotion intensity, this would increase the data quality and then facilitate learning. We get a better system. So the talk structure like this. We'll first present some methods to do weekly supervised extraction of emotion intensity from audio. Then we have some experiments where we train those emotion recognizers, how we extract the emotion intensity, and then train the emotional TTS model, and in the end, some conclusion and future work. So first of all, we didn't want to extract the emotion intensity by hand or do hand labeling. So we had the idea to use emotion recognizers to do this job. So we started with a rather simple one. It's a simple network based on an attentional STM network model. And you basically feed in some open smile features, a subset of it, and then you have a single attention block that gives you really just one attention weight for all frames. So T cross 1 here. And then you do a weighted sum, and from that you do your emotion class posterior. So here we thought that getting the emotion intensity is very easy because basically the frames that the network attends on are the frames where the emotion lies. So those are the frames that are most emotional and have the highest emotion intensity. Now, this network is slightly outdated, let's say. So basically right now in emotion recognition, people use transformer models a lot. So we also wanted to work with one of those models. So it works quite similar, has some open smile features that are going in, then some feature extraction part, and then it has two multi-head self-attention blocks, followed by a 2D convolutional stack to aggregate the features and some fully connected at the end. Now, the problem here is to say, what is the emotion intensity, or where can we get the emotion intensity from? Because you have this multi-head attention, so it's not clear which head we should use. You also get an attention matrix, so it's really not clear where this network attends on. And our idea to tackle this problem was to use saliency maps. So saliency maps come from the vision community, and they attempt to add some interpretability to the network prediction. You can do that at the input level. You can also do that for different layers or neurons. So here we want to do it at the input level, and there are a lot of techniques, and there are more and more coming out. We use some quite famous ones. We looked into input gradients, smooth grad, input X gradient, and integrated gradients. And what those techniques give you are those kind of important maps. So they tell you which pixels of your input image were the most important ones for making the correct class prediction. And you've probably seen those kind of images before. So for speech, for our transformer model, the input looks slightly different, but it's also two-dimensional. So we have open smile dimensions in one axis and then time in the other dimension. So you also get a 2D saliency map there. And what you actually want is you just want a single dimensional intensity value. So we also had to do some aggregation over the open smile dimensions. So here we looked into mean and max aggregation. So for the transform model, to get the emotion intensity, we use one of the input saliency map techniques, and then we aggregate with mean or max. We looked into one method from the literature, which is based on relative attributes from Perrotin and Grauman. So basically for each of your emotions, you extract phoneme level open smile vectors. So you first need some false alignment step for that. And then you form an ordered set O, where you have pairs of emotional neutral, and you form an unordered set where you put in pairs of neutral and neutral phonemes and emotional phonemes of the same emotion. And then what you want to do is learn a ranking function where you give some rank to the phoneme open smile feature vector. You want to satisfy as much as possible those two constraints. Basically, you want the pairs in the ordered set to have a higher rank for the first one. So in this case, the emotional one. And in the unordered set, you want to have similar rank. So it basically says you want a high rank for emotion and then a lower one for neutral, because the emotion one should have more emotion in it. Once you have learned this, and you can learn this by adding some slack variables, and you get a solution with Newton, which is very close to learning SVMs. Once you have that, you can compute the phoneme rank for all the phonemes. And then it's quite easy to say what's the emotion intensity. It's just the computed rank. So here you get some kind of step function where the emotion intensity is constant for each phoneme. So let's go over to the experiments we did. First, we trained the emotion recognizers. So we pre-trained on the EmoCap database because it's quite large. And then we fine-tuned on the Savvy database. We selected Savvy for our experiments because it has pretty high quality, which we thought is important for the TTS system. On the other hand, it's rather small. We worked with 6 categorical emotions, and we excluded disgusted in our experiments because it's very difficult to predict even for humans. So in terms of weighted accuracy that we got on the Savvy database after this training, for the attention LSTM network, we reached 62.5% accuracy, and the transform model got a bit more than 7% higher. So that is as expected, and 7% higher accuracy is actually quite a large gap in the world of speech emotion recognition. So, okay, we know that for the attention LSTM model, we want to use the attention weights. And we know that for the attribute rank, we just use the rank function. And this attribute rank was also learned by using the EmoCap database so that we keep it fair. Now the question was, which option do we use for the transformer? Because I already said we looked into 4 different saliency maps, and we had 2 different aggregation methods. And we also found that the saliency maps we got were rather noisy. So we also looked into smoothing them. And this basically gave us 16 different variants of emotion intensities coming from the transformer model. So here I plotted 2 out of those 16 variants, together with the emotion intensity coming from the attention LSTM model in red. And you can see that sometimes all of them agree on where the emotion intensity lies, but sometimes only the saliency map techniques agree, or just two of the two techniques agree, and the saliency map techniques don't agree on each other. So I extracted all of those emotion intensity values with the 6 invariants and also the attention LSTM network. And then I trained a TTS system. And I'm going to speak about how to train that later and how that looks like. But first of all, in informal listening, I didn't hear any preference between the saliency map techniques on the transformer. But what I could hear is that using the emotion intensity coming from the attention LSTM was consistently better. So basically, when we use the attention weights, we generally get better results. And we cannot compare against all the different saliency map techniques simply because our resources for the listening tests were limited. So we really wanted to compare against the best saliency map technique on the transformer. Why? Because the transformer was the better emotion recognizer. You remember that it had 7% higher accuracy. So we thought when it's the better emotion recognizer, it should also give us better emotion intensity values. So we had to make this assumption here that basically the saliency map that's closest to the attention weights in the attention LSTM model would also be the best saliency map to be used in the transformer model. I guess this is debatable, but this is how we made our choice on which saliency map to use. In this case, it was the smooth grad saliency map with mean aggregation and the smoothed version of it. So now let's speak about how to train the TTS system. It was a classical bi-LSTM-based acoustic model, so no encoder-decoder. The input were context vectors, HCS-style questions. We used oracle durations because duration prediction is very difficult for emotional speech, so we left that out at first. And the model predicts world vocoder features with deltas, double deltas, smoothed by MLPG. We use also world for the vocoding. Now the interesting part, so we use mean variance normalized oracle emotion intensities, and we concatenate them to the input of every layer. For neutral, we put the emotion intensity to 0. So why oracle here? Basically, we didn't look into generating the emotion intensity for now. We tried to establish like an upper bound on whether a TTS system would improve with this kind of emotion intensity information. And then once we see that this actually works, we can think about generating it from text or getting it from somewhere else. So as Savvy is very small, we also had to pre-train on another database here where we used Wall Street Journal Camp 0, and then we fine-tuned on Savvy. One reason why I used the classical approach here and not the encoder-decoder network is that I could simply not get it working on the Savvy database. The decoder would overfit the emotion fairly quickly because it's so small. So then we ran some subjective listening tests. Basically, in the test set, you have the same 2 utterances for each speaker for each emotion, so that the utterance content doesn't reveal the emotion. So basically, we just had 8 samples per emotion. Then we had 36 listeners. For each of them, we randomly selected 25 samples, which they had to rate. First of all, they rated the emotion they perceived, and those are the results you see here. So this is the accuracy in percentage, and basically total means over all emotions. And then emotional means just over all, but the neutral one. And you can see here that for the baseline system, without any emotion intensity information, the people were able to predict or to hear the correct emotion in 17.6% of the cases. On the other hand, when you run copy synthesis, you get up to 40.3%. So not super good, but yeah, world vocoder has its issues. So we found that with the attention LSTM model, we could actually push this quite a bit to 28.9% of the cases. And we also saw the improvements that were reported for the rank. So we also got a bit better results than the baseline here, the transform model as well, but not as good as the attention LSTM network. You can also see that for some emotions, it works fairly well. For example, for anger and for sadness, it helped a lot. Happy was not perceived as much here. This might be a reason because of the utterance itself, but yeah. So after this, people also had to rate the audio quality on a 5-scale MOS test where we had 0.5 steps, and we didn't see much difference there. So people also rated the copy synthesis quite low. Even though the world vocoder copy synthesis sounds quite different, people also didn't like it and rated it rather small. So we don't see any difference there. So here are some samples to play. Basically, this one should sound angry, and you will find that the baseline system doesn't sound so angry.
Shed your dark suit in greasy wash water all year.
Then the attention network, so the one with the emotion intensity from the attention LSTM network, which should sound more angry.
Shed your dark suit in greasy wash water all year.
Then the transformer model.
Shed your dark suit in greasy wash water all year.
The rank function.
Shed your dark suit in greasy wash water all year.
So they are probably between the baseline and the attention and the copy synthesis.
Shed your dark suit in greasy wash water all year.
So then one thing I didn't speak about yet is scaling. Basically, what we did at inference time is that we scaled the immersion intensity. Basically, when we just use the same immersion intensity as during training, we didn't get so expressive results. So, but as we now have the immersion intensity input in all the layers, we can actually just multiply it with some scalar. So I'm going to play this for angry here. So this is without scaling.
Shed your dark suit in greasy wash water all year.
Scaled by 4.
Shed your dark suit in greasy wash water all year.
Scaled by 7.
Shed your dark suit in greasy wash water all year.
And scaled by 10.
Shed your dark suit in greasy wash water all year.
I think I still have a lot of time, so I'm going to play also the fearful ones.
Don't ask me to carry an oily rag like that.
Then scaled by 4.
Don't ask me to carry an oily rag like that. Don't ask me to carry an oily rag like that.
And scaled by 10.
Don't ask me to carry an oily rag like that.
Okay, so maybe you heard in the last one in fearful scaled by 10 that the audio broke a bit. So we found that 10 is a bit too much. So for our listening test, we used 7 for all the systems. And the scaling you heard here is with the immersion intensity from the attention LSTM network. And there are some more samples to listen to on that webpage. Okay, so let me conclude this part. So we proposed 2 techniques for weakly supervised extraction of the immersion intensity with an immersion recognizer network. We used once the attention weight from a simple attention LSTM network, and then we proposed to use saliency maps for a transform model. We were able to demonstrate our hypothesis that the immersion intensity actually improves the TTS system, and we didn't hear any degradation in signal quality, at least at this rather low level of the world vocoder. Now, for the future, we would love to repeat the experiments with an encoder-decoder architecture and a null vocoder, but we would really require much more emotional data there, and I really think that this is not publicly available right now for emotional TTS. Also, now that we know that the immersion intensity brings a lot for the TTS system, it would make sense to look into generating it from text, or maybe getting it in a speech-to-speech translation task in one language, and then carrying it over to the other language. The code for this experiment will soon be ready here. Okay, thank you for your attention.
Thank you very much. Are there any questions concerning this paper? I would like to ask you, this is a weakly supervised or unsupervised way of detecting emotion. Did you make a comparison with a supervised version, or because of the lack of such kind of database, you couldn't do it?
Well, that would mean that we hand hear myself. Okay, that would mean that we hand label the immersion intensity for some utterances and then compare them, I guess. Then we would have the supervised way, and I did do that. I didn't compare with hand labeling. I guess this would require some experts do that, I think.
Other questions? Chat box, Géza? No. Thank you very much for your presentation.
Thank you.
The next presentation will be done by Slava Shechtman. Acquiring conversational speaking style from multi-speaker spontaneous dialogue corpus for prosody controllable sequence-to-sequence speech synthesis.
Well, do you see that presentation?
We can see
Everyone
it.
hear me?
We can see you. We can see you and hear you. Yes.
Okay, thank you. Hello everyone. Happy to see you here. Only one correction. My name is Avech. Slava is my collaborator. I'm a master's student at the Technion in Israel, and I will be presenting a joint work with Slava from IBM Research on acquiring conversational speaking style from multi-speaker spontaneous dialogue corpus for prosody controllable sequence-to-sequence speech synthesis. So first of all, some motivation. Companies need voice agents for customer care, and they would like to give their customers a feeling that they talk to a human. But modern commercial solutions offer neural text-to-speech, or more briefly TTS systems, which speak with reading style. Our research question is therefore whether we can make those systems speaking in conversational style. The direct approach, end-to-end training, has one major limitation. It requires a lot of high-quality data, and this is expensive. Instead of training from scratch, we suggest modifying a reading style system via prosody controls learned from public spontaneous conversations. And I would like to play some example only to give you a feeling what we can do with the noisy public data.
Hello, sir. Yes, I'm sorry to keep you waiting. I was calling from work, so that was a call waiting.
So this was a realization of our base systems, and ours is.
Hello, sir. Yes, I'm sorry to keep you waiting. I was calling from work, so that was a call waiting.
So I guess that you also observed that our realization sounds more natural, as it is reflected in the crowd scores marked next to each example. So recent work done by Gábor from Microsoft Asia demonstrated the end-to-end training of conversational TTS. They integrated BERT for processing the dialogue context, pre-trained on standard reading style corpus, and fine-tuned on 3 hours of specially recorded conversations. And as mentioned, we try to avoid this cost of recording professional speakers. Regarding prosody control, there are work like Mellotron that has shown ability to generate singing and highly expressive speech by forcing prosody features in high resolution. However, in our case, we attempt to learn from public and unfortunately noisy data, thus only high-level prosody features can be obtained. In this work, we make use of a prosody controllable TTS system trained on standard reading style data. And we integrate conversational styles via high-level prosody controls learned from noisy multi-speaker spontaneous conversations. So how our prosody controllable TPS looks like. We built on a previous work in which Tacotron 2 architecture was trained such that one can modify some prosody features like word and sentence duration, pitch, and some more. As this base system is described in detail in the specified paper, I will focus on our novelty. But the only one important detail is that the system was designed so that one can remove the default prosody predictor, which generates reading style features, and play the system with arbitrary input values. Our core idea is to train a neural model in red to predict context-aware prosody controls. We let our model look on the chat history and train it to predict high-level features which can be extracted from arbitrary conversations. Finally, what are those prosody control signals? Similarly to the previous work, we defined a hierarchical prosody control, in brief HPC, as a sequence of word-level features. The table on the right side represents a sequence of columns where each column corresponds to a word in an arbitrary utterance, and each cell represents a potentially different value. In this example utterance, we have two sentences, the first with 3 words and the second with 2 words. A front-end module inserts silence words in certain places in the text, generally where commas and period signs appear. Each word is assigned 6 features, where 3 are constant across a sentence, and the other 3 features can change across words. The blue and red colors distinguish between regular words and silence words. We allow modifying the duration, average pitch, and the average pitch slope of the word, and similarly in higher level for the whole sentence. Silences require only duration, so their pitch-related features are just ignored. For demonstrating how we predict such a sequence for a given sentence and context, let's look on the following toy example. Consider a sentence with 2 words and a single intermediate silence. The text will be W1, comma, W period, and the corresponding HPC has the structure shown in the red square. And let's see how our model predicts this HPC. So our model has an encoder-decoder architecture. The encoder inputs are the target words, W1, W2, and these words we want to synthesize. And optionally, the context, text, and audio. The decoder outputs the HPC sequence we just defined. So the encoder comprises 3 modular blocks through which it encodes the target words. Similarly to previous works, we integrate a pre-trained BERT model and leverage its knowledge to encode the target words in the context of the chat history. We work with BERT in the question answering mode and set the dialogue context. The dialogue context is fed as the question part and the target words as the answer part. From the output tokens, we select the first token per word to form some word representation P1 and P2. In addition to the semantic processing made by BERT, we pass the target words through the TPS phoneme encoder and learn phone level features which are averaged then to word level representation P1 and P2. We also hypothesize that there is interesting information in the context audio that cannot be expressed by text, for example, sarcasm. So we extract the HPC sequence of the context dialogue and learn prosodic context representation marked by PC. All those 3 representations are combined and encoded as WE1 and WE2. Our decoder takes these word representations produces sentence level features by averaging. Word level features are generated straightforwardly. And to generate silence features, we consider the preceding word encoding of each silence as a silence representation and predict the silence duration using the third MLP block. Now we just need to combine those features to form the HPC sequence. I encourage those of you who are interested in the implementation details to read our paper. So the data set we are training on, as claimed, we attempt to learn from public data. So the data we dealt with is a switchboard originally recorded for speech recognition tasks. This data set contains thousands of spontaneous telephone conversations organized in turns, and they were held by hundreds of English speakers. The data is super challenging, full of filler words, burst-ins, pauses, repetitions, and many more real-life interruptions. In order to estimate the context importance, we define several context windows. The first is, of course, no context. This is the naive option, or not. Maybe it's okay. The last turn, we consider the last turn as a minimal context window, and a wider context window which goes back until covering the last turn of the other speaker. In this example, you can say the sentence, did you tell your parents already, with the severe tone, getting to an accident case, or with excitement, as in the case of a new job. So our experimental setting, for training, we extracted 176,000 valid examples from switchboard. I mean by valid example that they contain all the relevant information after word alignment, all the preprocessing needed. We trained the model to minimize the weighted MSE loss of the sentence, word, and silent output, and selected the best models by listening to 35 validation examples. We conducted the subjective test to evaluate the mean opinion score of 25 held out examples. Each stimulus received at least 30 evaluations. We evaluated the overall quality and naturalness, and separately the style and style adequacy to the given context. So we get to our results. These are the numerical results. The table on the right presents the mean opinion scores for 6 models. In addition to the mean opinion scores, we report the percentage of better than baseline examples. It makes sense because we have multiple evaluations per stimuli. Just for explaining the abbreviations, BASE is the default TTS without any prosody control. PHN refers to predicting HPC based on the phonetic sequence of the target words. BERT refers to predicting HPC based on BERT features, of course. And the additional abbreviations, TC specifies that we use textual context only with BERT. And the TPC specifies that we use the textual context with BERT and also the prosodic context. You see here 5 models, part of the base model. The ablation study results show that BERT is the critical component here, while the phonetic sequence and the prosodic context did not help and even degraded the performance. The phones only model completely failed. We explained this by that the training data was super challenging, and the fixed pre-trained phone encoder that was trained on clean reading style data could not produce useful features. As for the BERT-based models, BERT TC and the BERT PHN are very close in the total mean opinion scores. It implies that BERT can perform very well without context at all. Exploring the best models stimuli and their corresponding scores, we found that the improvement came from better realization of common conversation patterns such as filler words and phrases, and mostly at particular text-to-add patterns. This explains why text only was enough to gain this improvement. In close analysis of the BERT PHN models, we found that adding the phonetic input led to expressiveness deterioration, and as a result, lower count of better than baseline mean opinion scores. However, the terminal sentence prosody was improved so that the total score is similar to the baseline. The last question we should answer is why the total mean opinion score of BERT-TC does not reflect the considerable count of stimuli that improved over the baseline. We observed that our model was consistently downvoted on uptalk style, which is rising intonation on declarative statement end. This style was acquired by our HPC model, but though this style is common in spontaneous speech, our TTS synthesizer was not exposed to such examples when training on the reading style data. And the realizations were not convincing. So I want to play some example. I will focus on the best models. So first, the questions were consistently improved. Let's hear the base model.
But you're going to manage to make her stick to your plan, right?
So we heard that the right at the end doesn't sound well. And our best model sounds like...
But you're going to manage to make her stick to your plan, right?
Much better. Filler words also improved.
Well, I mean that's good, part-time money.
And the rest of the models.
Well, I mean that's good, part-time money.
And a failure case on the uptalk, we can hear the bass.
I wasn't aware of that. I thought they were more or less all the same.
And our model tried to raise the intonation at the end of the sentence, and it sounds like this.
I wasn't aware of that. I thought they were more or less all the same.
So you can realize that the realization sounds unnatural, and it might be because our synthesizer that just doesn't know to produce this effect. So I encourage you to visit our website and listen to more representative examples. And I'm not aware of the time, but I guess we're almost done. I will just move to the conclusions. We demonstrated how to apply conversation style to reading style systems using positive control learned from spontaneous noisy data. And this method mainly improved common conversational patterns. On the other hand, the improvement was not statistically insignificant. And the possible reason for that is the trends that were not seen during the synthesizer system training. We plan to investigate merging the conversational HPC with the reading style one to eliminate undesired artifacts such as uptalk. And And in addition, we consider the interesting fellow cases we found in this cheap experiment in the design of a new conversational corpus. So thank you for listening, and I'm here to answer your questions.
Thank you, Slava, the talk. Oh, I beg your pardon. I repeat. Yeah. Avrek Ben David, yes?
Yes.
Thank you. Thank you very much. Are there any questions here in the room? Expressive speech synthesis is not popular here in the audience. I would like to ask you two questions. How many question types did you have in your database? Or because, for example, in Hungarian, there are a lot of question types, and all question types have their own F0 form. This is my first question. And the second question, and the second question is what can you imagine to solve this uptalk problem?
Okay, your first question about how many question types, it's hard to me to answer. I'm sure my colleague knows to answer how many types were existing the reading style data they used for training the base system, but in the switchboard data, I don't know how many question types there are. It's a completely spontaneous corpus, a huge one, and we didn't really analyze the data in such a resolution.
There's one question in the chat box. Do you see that? Thank you for your presentation. Have you considered using output of BERT as it corresponds to the continuity of conversations? The question is about continuity.
We were interested in word level features, but not in the overall representation of the context or the target sentence. So we did not consider using the CLS output, only the word level features.
Any other questions? Thank you for your presentation.
Thank you very much.
Ladies and gentlemen, the next talk will be presented by Bastian Schnell, EmoCat, Language Agnostic Emotional Voice Conversion. Please.
Thank you. Okay, so this work was performed as part of an internship at the Alexa TTS Research Group in Cambridge. So basically, motivation is similar as in the previous talk. Basically, when you work on emotional TTS and you're limited in high quality emotional databases, there are like three things you can do. You can increase your model generalizability by being smart about your model, using VAEs, intercross training, this kind of thing. Then the second approach is to use to increase your data quantity by using, for example, unlabeled data, as in audiobooks, or by using artificial data. And that's what we are trying to do in this work. So we want to generate more emotional speech to then later train a TTS system. Third approach would be to increase the data quality, as in the last work that I presented. So the goal for this work was to enable German emotional voice conversion with rather low amounts of emotional data in German. So basically what we want to do, what was the use case, was the conversion from neutral to disappointed and excited emotion at 3 different intensity levels, so low, medium, and high. And the hypothesis for the work was that emotion is produced in a similar way between English and German. So that when we want to generate an emotional voice conversion system in German, we can also exploit large amounts of English emotional data, which we already have. So the overview over this presentation is as follows. I first will present the model architecture. I will then speak a bit more about the emotion embeddings we use, and then present the gradient inverter block, which is basically our novel approach for the gradient reversal. Then I will play some samples and in the end conclude and show some future directions. So the EmuCAD architecture is like this, and it mostly resembles the copycat model. And copycat itself is highly inspired by AutoVC. So basically what you have is an autoencoder structure. So here on the left side, you have the encoder part. You give in some source emotion spectrogram. You have a VA reference encoder and a bottleneck encoder. And this bottleneck encoder is the same as an AutoVC. So it's temporal and also dimensional. Then you give those bottleneck features to your decoder part, which is this part here. And we use a parallel decoder. And this decoder is also conditioned on the phoneme sequence. And this is already upsampled. So you have done the forced alignment step there, and you have the correct alignments. Both are also conditioned on the emotion embedding for the source emotion spectrogram here. And you can use the target emotion embedding centered here at inference time. During training, you would use the same emotion embedding as here and there. So in contrast to copycat, you basically just replace the speaker embeddings by utterance level emotion embeddings. Now this model is trained with German data. So first of all, we had more than 20 hours of neutral speech and 45 minutes of emotional speech. And this basically means that for the high excited, which is the most challenging emotion here, we had only 5 minutes of recordings, single speaker. What we also had was English data, and there we had more than 20 hours of neutral data, but also more than 10 hours of emotional data. So a lot more. And we are using disjoint phone sets here, so that's why we don't need any language ID or something. So the utterance level emotion embeddings we use are pre-trained. So we don't train them with the EmuCAD model together. We first train rather classical tachytron structure model that looks like this. We just have 2 additional reference encoders here, one to encode the emotion and one to encode the speaker, which are guided by some extra classification loss here. And basically, we want those emotion embeddings to be language independently. And we achieve this by using inter-cross training in this model. And we want them to depend only on the style and letter information. So this is why we chose this structure here. So yeah, I already presented this. Now, when we trained this model first time, we found that there was quite some leakage. Basically, the conversion didn't quite work. And in AutoVC, the suggestion is to decrease the size of the bottleneck, but that only impaired our audio quality. So we wanted to figure out whether there's actual leakage. So we put this immersion classifier here, and we kept the rest of the network as it was trained. And we trained only the emotion classifier. We tried to figure out if from the bottleneck features, you can infer the emotion class. So we trained this for like 10,000 steps and on a subset of the training set. The results, what we got was like this. So we first looked into a variety of classifiers. So that we make sure that we have one that really works. We looked into simple feed-forward layer, then some bidirectional GAUs, also an LSTM, CNN structure, and a CNN plus some GAU where we use the last state. And we found that with the feed-forward classifier, it only predicted neutral all the time. So it basically wasn't able to predict the emotion from the bottleneck features. So neutral in this case was the majority class. The best classifier we got was simple GAU. We used the last state, and it had 128 neurons. And this is the confusion matrix of this classifier. And I want to raise your attention to basically this. So here are the emotions. So high disappointed, medium disappointed, low disappointed, neutral, then low excited, medium excited, high excited. And we found that actually in 65% of the cases, the classifier was able to predict high excited just from the bottleneck features. And in 30% of the cases, it predicted medium excited, which is not exact same emotion as it is there, but it at least recognized that there's some kind of high or more higher excited content in it. So we definitely had a lot of leakage. So first thing we did was we applied a gradient reversal block with the same emotion classifier. Gradient reversal is sometimes a bit difficult to get working, so we tried different ways here. We always tried this kind of combinations. And we worked with the feed-forward and the GAU adversarial classifiers in different experiments. And then once we trained this, we again added this GAU emotion classifier and trained it independently from the rest of the network to figure out whether there was still emotion leakage. We found that actually this gradient reversal block with the emotion classifier effectively removed the leakage, but it even removed the leakage with the simple feed-forward emotion classifier. So the one that wasn't able to predict the correct class from the bottleneck features was still good enough to be used for adversarial training, which is, I think, an interesting result. So then from the gradient inverter block, we had some problems with that. So basically imagine this situation where you have your bottleneck embedding and you have a lot of leakage of information. So then it passes through the gradient reversal block and you give it to your classifier, your emotion classifier. And this one can do a very good prediction because you have a lot of leakage. So you get a very low cross-interpreter loss on the outside. Then this is all passed back and you get a very small gradient. So you have quite some leakage, which you want to remove, but the gradients you get is quite small. Now, in the other scenario where you don't have any leakage, your emotion classifier can make a good prediction because there's no information in the embedding, and you will get a very high loss. And when you backpropagate this, you actually get back a big gradient. So even though you don't have any leakage in your bottleneck embeddings, you still change your embeddings a lot, and you have a great effect on the rest of the network, even though you don't have to change anything at all. There's no leakage. So vanilla gradient reversal looks like this, right? You just flip the sign basically, and you add some weight. Now, our idea was to actually make big gradients small and small gradients big. So we came up with the idea to scale with the inverse of the squared norm. And as a second approach was the inverse of the exponential of the squared norm. So I've plotted those two functions, and basically what you can see is that everything which is smaller than 1 in norm is quite big, and then anything which is bigger than 1 in norm is faded out. And basically with the inverse square norm function, it didn't quite work everywhere, because basically for very small norms, you get this explosion here, which is not very stable. That was one reason we came up with this second inverse exponential square norm function. So let me play some samples now. So basically this is how high disappointed should sound like.
Der Rest war einfach nur peinlich.
And then this is the neutral utterance we want to convert.
Aus für Schirmmacher, Revolverdreher und Schiffszimmerer.
So without adversarial training, this doesn't quite work.
Aus für Schirmmacher, Revolverdreher und Schiffszimmerer.
Then vanilla gradient reversal.
Aus für Schirmmacher, Revolverdreher und Schiffszimmerer.
and with the square norm function.
Ausführschirmmacher, Revolverdreher und Schiffszimmerer.
So this should sound much more disappointed. On the other hand, this one doesn't sound so good.
Ausführschirmmacher, Revolverdreher und Schiffszimmerer.
Then same for high excited. I first play your reference sample.
Ein wunderbares Durcheinander von Klängen.
Okay, then maybe this one as a neutral one.
Gewann vor Rob Huff und Alain Menü.
Without any adversarial training for high excited.
Die Match Races, bei denen jeweils 2 Boote gegeneinander antreten, werden in der Kieler Bucht ausgetragen.
With vanilla gradient reversal.
Gewann vor Rob Huff und Alain Menü.
Oh, that must have been the wrong one.
Gewann vor Rob Huff und
With
Alain
the exponential
Menü.
square norm function. And with the square norm function.
Gewann vor Rob Huff und Alain Menü.
So for high excited, we actually found that this one works better than this one. And here we're not sure whether we got quite high intensity and the vocoder broke maybe, or the system broke there, or if the network if that function really is not working so well there. So then we did muster evaluations. We looked into some competitive systems which were based on stagger. Unfortunately, they were using world vocoder features, and we used our neural vocoder, so it didn't really make sense to compare against it. And I tried to train the Stagan with the MEL frequency features, but that didn't quite well, so the structure didn't quite work. So the structure of the Stagan would need to be changed to actually get a network that works with it. So instead, we did an ablation study where we compared gradient reversal against our gradient inverter block, where we used the exponential square norm function for excited and the square norm function for disappointed. And with that, we also looked into fine-tuning. So for fine-tuning, we used only the German emotional data and an equally small amount of neutral data, and then fine-tuned on that for a couple of iterations. So those are the results. Basically, for just for excited emotion, are those the results for emotion intensity and audio quality? So first of all, our gradient inverter block is only better than the gradient reversal for medium excited. For low excited, it's a bit worse, and for high excited, it's equally good. So when you have this bar up here, that means that there is no significant difference between the systems. What we also see is that we have a gradient of emotion intensity. So we got here like rather small or low excited, and then higher and even higher. But at the same time, we are not reaching the recording level yet. For fine-tune, that didn't help. We don't see improvements in emotion intensity. It even degrades it. And there's no improvement in signal quality at the same time. So it didn't help us. And what we found is that the audio quality that we got for low and medium excited is at par with the recordings. But for high excited, we are still not there. At the same time, for disappointed, we see that the gradient inverter clearly outperforms the gradient reversal block here. It's better by quite a lot for all the different intensities. We again see that there is this gradient, which is still for the higher disappointed levels, not quite with the recordings, but at least we get this gradient here. For fine-tuning, we got the same results. It didn't help here. We didn't see improvements in audio quality. And the audio quality of all the systems was at par with the recordings. Interestingly, the listeners found that the neutral production system sounded better than the recordings in terms of audio quality. So our hypothesis here is that might be because those were like acted emotions in the recordings, and that people found it slightly unnatural, and that they actually found it. That's the reason that they didn't like the audio quality as much as a neutral production system. So let me conclude this part. Basically, what we proposed is a language-agnostic emotional voice conversion model for German. We leveraged a lot of emotional English data, and that helped to train the emotional German model. We found that the gradient inverter block that we proposed outperforms the vanilla gradient reversal in 4 out of those 6 emotions we tested, and we only saw limited success with the data fine-tuning. For future work, we call this language agnostic, and in theory it should be, but we've only tested on quite similar languages, right? English and German. So it would make sense to test this on more diverse languages. We've also seen that we have 2 different gradient inverter functions, and maybe we did not find the best one yet. Maybe there's one that works good for both emotions. Then we did not yet reach the expressivity of high excited. That is still to work on. And it would make sense to look into different styles. The model should be able to convert also to other styles like newscaster or conversational speech. And one thing that the model doesn't do is duration modeling. So basically the number of frames that you put in doesn't change much. It doesn't change. So the network can only make the speech a bit faster or a bit shorter, but it's quite limited. And what is of course left is training a TTS model with the generated artificial samples. So thank you for your attention.
Thank you very much, Bastian. Here in the room, are there any questions concerning this presentation? Please come here.
Good afternoon. I just want to ask a question regarding the baseline selected. So why is it that you tried the Stargam baseline instead of a Cyclogam baseline, which has been previously used in emotional voice conversion, and it also works with the word vocoder features, as far as I'm concerned.
So when was that released? The one you speak about, because this is work from last year. When I looked around, the best model I found was the Stargam implementation. I think even that there is now a Stargam implementation with mouse spectrogram.
Oh, so you use mouse spectrogram features, or you use word vocoder features, just to clarify this point?
Mouse spectrogram with the neural vocoder.
Ah, okay, I see. Thank you.
There's a question, a chat question. Do you see it? How did you decide to use disappointed and excited?
Well, that was the use case we had for the Alexa voice, or for the Amazon internship.
Any other questions, please? I have a question. If you said that less similar languages will be planned in the future, what do you need to adopt the system for a Hungarian, for example, or for a Slavic language? Only an emotional database, or some fine-tuning, or some other processes are necessary?
Well, I would hope that I just need the same amount of like 45 minutes of emotional Hungarian and a lot of neutral to get this working. But yeah, I don't know. It would show. In theory, it should work the same way, right?
Thank you. Thank you very much for your presentation. Now, ladies and gentlemen, The fourth presentation will be shown by, I don't know, the first author is, this talk is Abdelhamid Ezerg, who will be presented this presentation. Mr. Klimkov, perhaps, I don't know. The title of the presentation is Enhancing Audio Quality for Expressive Neural Text-to-Speech. Please, you are on the floor.
Hi, everyone. Can you hear me?
We can hear you. Thank you.
And can you see my screen, actually?
We can see it, yes.
Okay, thanks. Okay, so hi, everyone. My name is Abdelhamid, and I'm an applied scientist at the TTS research at Amazon. So today I will be presenting our work that we did for enhancing the audio quality for expressive neural text-to-speech. Yeah, so this is an overview of the presentation. So first, it will be a brief introduction of what's the problem at hand. Next up, we just discuss the proposed techniques, and the last section will be for the experiment and the results. So now looking at the problem at hand, or the problem statement. So it's quite pragmatic, like we basically want to build a TTS system for an expressive celebrity voice. So when we say that the data set is expressive, this is basically was measured through subjective listening tests or through some heuristics. So for example, we can look at the variance of F0 or energy or phoneme durations within the data set. And it was like a high for this celebrity voice compared to like other voices that were productionized in the past. So this is like why we say it's more expressive. And yeah, like we can say, like we can see that like there were different prosody variation in the data set. So that's for that particular speaker. Now, because like it's a celebrity speaker, we had like a bit of a more limited data set compared to other productionized voices. And when we trained the baseline use that limited data set, what we observed, like we observed two types of issues. So first were like instabilities in the synthesized speech. So this is like more related to the attention mechanism failures, like for example, speech that cut off too early or some mumbling. So these were like the first family of issues that were observed. The other family were more about like harshness. So more like the speech sounds a bit noisy or like a bit of creakiness in the voice. So this is like the problem statement. And in terms of objective, what we want to do is pretty simple. So the idea is like we want to keep the level of expressivity, but we want to improve on reducing these issues. Like we want to reduce the instability issues and we want to improve on the audio quality. And like the constraints that we have is that we don't want to ask for more data, because of course, like you can just like ask for more data and train on that, but we had to use just like that limited data set. So this is for the problem at hand. Now moving on to the proposed techniques. And here it's an overview of the architecture. So it's a Tektron 2-like architecture where we have a phoneme sequence that goes through phonetic encoder, attention mechanism, autoregressive decoder that produces the Möller spectrogram. So this acoustic model has been reinforced by the use of a VAE encoder. And yeah, the output spectrogram goes through the neural vocoder, which produces the waveform. So till now, I think, yeah, it's like more or less like a standard procedure or standard architecture. But we will be diving into each of the techniques right now. So the first one of the techniques that we have used for improving the quality was tuning the autoregression. And here we are targeting mostly this block in the red box. And yeah, so the autoregressive decoder is autoregressive because like when we are predicting the spectrogram, here spectrogram is denoted as Y. When we are predicting the spectrogram, like each prediction is a function of the previously predicted frames. So this is like, yeah, that's like a standard autoregressive decoder. What we did observe like when we are predicting one frame at a time, we had a high quality of speech. So in terms of like this noise or the harshness, like there weren't much in the speech. However, like we had a high number of instability issues. So like the attention loss and mumbling. So what we went with, like it was like a different approach, like maybe just like synthesizing 5 frames at a time instead of 1. And here like it is more stable, but it's the other way around. So it's more stable, but like we have more issues in terms of segmental quality. And here just like a quick diagram showing what we do. So yeah, we have like the decoder cell. It's just like its initial frames. It predicts 5. These 5 go into the next cell, and all of these five chunks get like concatenated to produce the full spectrogram. So the idea, like this comparison between 5 frames and 1 frames, like in the end, we just like want to achieve like the best between both worlds. So having high segmental quality, but at the same time being more stable. And the idea we had was just basically tuning this number of predicted frames from 5 potentially to 1, but actually after some tuning, we stopped at 2. So how does the tuning process work? Since basically we need, basically it's the same architecture, so the weights need to be of the same shape. What we do instead of, we predict still 5 frames at a time, but this time we just selected the first 2, we pass them into the fully spectrogram, but we ignore the other 3. Then we move by 2, we pass them, we ignore the other 3, and so on. So this will require more decoder steps than the 5 frames, but it requires less steps than 1 frame at a time. And overall, in terms of the performance, it was like the best in terms of the segmental quality versus the stability trade-off. So this is for the first technique. Now I'm moving on to the second one. So second one, I think this is quite standard now. So the acoustic model basically uses phoneme sequence. If we ignore the VAE encoder, like the model just has the phoneme sequence, which means it lacks like some latent factors or prosody representation that are not stored in phoneme. And this is like why we add this VAE block basically to help factorize these latent representations and latent factors and basically help direct the synthesis. So yeah, we use like a reference encoder, which is a stack of convolution layers plus bi-LSTM. And yeah, basically we produce the latent representation that gets passed to the rest of the acoustic model. One thing that's like we tried in particular for this, it's like what we do at inference time, because at inference time we can, for example, at training time we use the original spectrogram to get latent, but at inference time what we do. So there was the first scheme, which is like the default one of just using the 0-1 Gaussian and like the prior distribution sampling from there. The other scheme that we actually have tried is also trying to do some more careful selection of the reference utterance. So for example, when you want to synthesize a question, you go to the training set, you select a question utterance, you extract the latent representation, and you use that instead of sampling. So we did that, and like it was like we had a question reference for questions, neural reference for neutral reference for neutral speech, and so on. And actually, like after some listening tests, it like yeah, we went for the second scheme because like it did perform better for us. Yeah, so this is for the second technique. Now I'm moving on to the third technique. This was like GAN usage. So we wanted to leverage the generative adversarial network. So here in the acoustic model, we are talking about the part that goes from phonetic sequence to the spectrogram. So we are ignoring the vocoder. We get the predicted spectrogram. And here we take a window, like we sample a window of the spectrogram and pass it to the discriminator. And the discriminator's job is to determine if it's real or fake. So it's, again, like a standard GAN setup. The only thing worth mentioning is more like we tried also with putting the full spectrogram, but like it didn't perform as well as just like taking a sampled window. The hypothesis is that like by taking the sampled window, the discriminator is more focused onto yeah, this noise, which will affect more like the segmental quality, and you don't need like the full context for that. Here I just like put the losses just to have an idea. So the discriminator is basically trained using a hinge loss, which basically just tries to make sure that the fakes are detected as fakes and the real spectrogram is detected as real. And for the generator, the overall loss looks like this is like L1 or L2, like this is the standard used for training Tektron 2 like architectures. We add then the adversarial loss to make sure that the generator is actually full in the discriminator. And the last part, this is the VAE loss. So it's annealed because like to avoid KLD collapse, we had to do some annealing, but more or less, this is how the loss looks like. So normal generation part, adversarial loss plus KLD loss. But yeah, it more or less, it looks like a standard GAN procedure. Now looking for the final part or the final technique, it was conditioning the neural vocoder on the VAE output. So here we are, again, like this is the original architecture. And here we are targeting this component in the red box. So the idea, basically, we just like take a neural vocoder, which is similar to the parallel wavenet one. And the only change is that we take the VAE latency representation that we concatenate with the conditioning to produce the output. So this seemed to help greatly with the performance. And we were thinking like why it does help. So one of the hypotheses we had is that this is something that makes the training and inference time close, training and inference mode close, or less mismatch between the two distribution. Because for the vocoder, at training time, it sees the real spectrogram, but at inference time, it sees the predicted one. So there is this mismatch. When we provide the VAE, we have like this additional information that like says where in the acoustic space you should be, but it sees like less mismatch between inference and training mode. So this was like one of the hypotheses. And here I linked a paper which is discussing this into more details, and it's like a different paper done by the team. So this is for the overall techniques that we have used. So I will move on quickly to the experiments and the results. So in terms of the experiment, so we basically took a data set of this English-speaking celebrity voice. We trained two systems. We have the baseline and we have the full system, which is basically baseline with the application of these four techniques. And we sent them in a Mashra test. So the Mashra is around 160 utterances, and each was rated by 15 native English speakers. And seems like, yeah, we have like a significant improvement, which is around like 39% gap closing between the baseline and the recordings in terms of what the full system did achieve. So this was like pretty encouraging results. Moving on to the next part, we didn't only look for naturalness, we also tried to look for trying to count the number of issues we had. So we went for a voice quality assessment. So for the voice quality assessment, we gathered around 275 utterances. Here we tried to look to challenge the model. So we had like utterances of different lengths, ranging from short to very long utterances. We also had like different domains like spelling, which used to be challenging, questions, just neutral utterances, newscasting, and so on. So we tried to like go for different domains to challenge more the model. And overall, in terms of the performance that we got, in terms of the base, like we reduced like all of the critical issues. So for the critical issues, this is more like this attention instabilities or like mumbling or the cutoff of speech. So we reduced that, and actually we reduced a lot like also a number of medium issues. These will be like more related to the segmental quality, like noise and harshness and so on. So this was the results of the test. And the final part was like doing an ablation study. So basically we took the full system and we removed each of the components to see like how much they impact the score. And in terms of trying to rank the impacts of each of the systems, I think the first ones like were the VAE conditioned neural vocoder. So this one like helps a lot. So this was like the last technique that was discussed. And before that, there was the auto-regression tuning. So as well, this one was very helpful. It didn't, and the last part were the VAE in acoustic model and the GAN training. So these two helped, but they didn't help as much as the VAE conditioned neural vocoder and the auto-regression tuning. So this is more in terms of the techniques. Overall, as a conclusion, like in this paper, we just try to present a set of techniques that maybe like if you have a model and you have like this trade-off between expressiveness and the segmental quality, you can just try and play with these techniques and see if they can perform and help you. So that's it. Thank you very much for your attention. And yeah, please feel free to ask me questions. Thank you very much.
Thank you very much for your presentation. I ask again about the questions. There are no questions. One question is on the chat box. Thanks for your talk. Do you see it? Have you tried using a different model? Pardon?
Yeah, I think I can see the question. Thanks. Yeah, so in terms of using different priors, so for that particular experiment, no. So this is like something we have we started exploring, for example, when I said like we did this careful selection of the utterance to use as a reference. So I think like this is a good direction to go. But yeah, I think for this one, it was like still for this particular experiment, it was still basic. So we could actually try to extend it, use, for example, more hierarchical VAEs, or yeah, like use more advanced stuff. Because for now, it was just like simply yeah, just like using the 0-1 Gaussian for training, and at inference time, we were just like using this rule-based selection.
And from Bastian Schnell, when using a reference audio to obtain this question.
Sorry.
Did you have a similar problem?
When using to obtain a reference?
From Bastian Schnell.
Yeah. So actually, in terms of you mean like when using the reference? Let me think. So the idea was like having different lengths. I don't actually remember like if we noticed this. So having like different lengths of sentences. So the idea, so we had like this reference embeddings, and I think this part like was a bit tricky because like we can use, for example, the reference embedding as it is, but sometimes yeah, like it was like you can just like use the mean, and like it would have been like a bit maybe more boring in terms of variation, but it was like a bit more stable in terms of synthesis. Here I would say I didn't like observe like or at least like we didn't look into did the length change, so I can't say for sure. But yeah, I think more or less like even like with this attention like models, like there were some differences in length between like what you would have gotten with teacher forcing and just like running synthesis without even talking about using the VAE. So I would say I haven't like observed that much, but yeah, I am not sure like I got the question exactly. Sorry.
There is another question. From Adam Foglia.
Mm-hmm.
Have you tried using a different model of the prior and posterior distributions in the VAE? What dimensions did you explore for the reference embeddings, and what attention model did you use?
Mm-hmm. So I think for the initial one about the priors, it's like what I answered earlier. So it's more, we just use the 0-1 Gaussian prior. And but like at inference time, this is like where we introduced this like rule-based selection of reference to use. Now in terms of like which dimension, okay. So in terms of dimensions, like where we were looking, I think it was mostly like handcrafted more or less. So like what we were looking for when selecting the utterance, if I understood the question. So the question is like what we were looking for selecting the reference. And here it was, if we are looking for example, a question, we know that we are ending with a high intonation. So here, like it will be easy, like we just like go to the training data set and select a question with like high intonation and select that. So this is like what's something that we use. Okay, so you meant the size of the embeddings. For reference, I think it was like a fixed size per utterance. So we were like summarizing the whole thing. And from memory, it should be around 256. The number might be not exact, so I can double check for you. But I think, yeah, it was just like trying to summarize the whole sentence in 256. And now about the attention, it was location sensitive attention. So we had like, yeah, we use basically location sensitive attention. There were actually some tricks to manipulate the weight, so like to avoid attention collapse or instabilities, but more or less it was the location sensitive attention.
Another question?
Mm-hmm.
Where the VAE encodings and so on, do you see?
Yeah, so the VAE encodings were at the utterance level. So future work can explore doing that like more phoneme level or doing some hierarchical VAEs. But for this work, it was more utterance level, and then it gets concatenated with the phoneme outputs, the phoneme encoders output that goes into the acoustic model. Thanks.
Thank you very much. Please.
Yeah, I was just going to ask about this VAE input to the vocoder, and maybe you could just explain a little bit more about the intuition there, and in particular, if it's just related to the distillation process, and it wouldn't really be necessary if you weren't using this teacher-student thing.
Mm-hmm. To be honest, yeah, okay, so in terms of intuition, like the initial intuition, it was more about, yeah, basically trying to reduce the mismatch of distribution. So as mentioned, during training time, you have this basically real spectrogram distribution. As inference time, you only see the predicted one. So from the neural vocoder perspective, that's a shift. And here, when we add the VAE, there is still a shift, but it just like there is a smaller mismatch. So I think like in the paper that I linked, like I didn't discuss this more here, but it was like shown that like this VAE would live like closer together in the acoustic space. And this is like why we think like it helps the model, because at least it has a reference that doesn't change much in terms of distribution. So this is like why we think it helps. In terms about the distillation process, to be honest, I am not sure. I didn't think about it in this slide, but overall, I would say the main hypothesis, at least for us, it was like the mismatch between what you see during training mode and inference mode. So I'm not sure if it's specific to just like using teacher students, or even like if we trained like, yeah, neural vocoders without like using the teacher student framework, that the VA wouldn't help.
Thank you.
Thank you.
Thank you very much. I think that I see that this was the most successful presentation concerning the number of questions in this afternoon. Thank you very much for
thank
your
you very much.
nice presentation.
Have a nice day. Thank you.
The next talk and the last in this afternoon will be done by Lucas H. Ueda, Brazil. Are we truly modeling expressiveness? A study on expressive TTS in Brazilian Portuguese for real-life application styles. Please.
Can you hear me and see my screen?
We can hear you and see your screen.
Okay. So, good afternoon, everyone. So, I'm Lucas. I'm from Unicamp, from Brazil. And the co-authors are Paula, also from the Unicamp. And this work was a collaboration with the CPQD Research Institute, also from Brazil, with the Flavio and Mario co-authors. So I will present our work. The title is Are We Truly Modeling Expressiveness? A study on expressive TTS in Brazilian Portuguese for real-life application styles. So I'll start by giving a brief introduction to the project. Then I'll talk about our data setup and the experiments that we perform. And finally, I will present the results and the conclusions. So several works have been applying the recent TTS architectures and the augmented ones with like style encoders to model expressiveness in speech. And when working with like emotional speech, like happiness and anger, for example, some of the works already seem to work well with this approach. However, only a few works tries to deal with non-archetypal styles of speech or related to real-life application styles. We then, in our work, we performed like several experiments using some of this recent approach, using these style encoders, applying to a non-archetypal style that we recorded and described as being associated with a real-life customer service application. And we call it like enthusiastic style that can be described as positively excited. So we worked with Brazilian Portuguese audios, and for neutral part of our data, we have 26 hours of neutral speech divided into 3 speakers, speaker 1, 2, and 3. Additionally, in our experiments, we separated a phonetically rich subset consisting of about 2 hours of speech per speaker. This subset has a good phonetic coverage, allowing us to train a TTS model with less data. Furthermore, with this reduction in the amount of neutral data, we can have a better balance between the neutral and the expressive speeches. About our expressive data, we have it only for the speaker 1, and we first recorded about 27 minutes of expressive data with a recording quality that we call medium quality due to a presence of certain reverberation that I will play some example now.
Se quiser ler bom livro, tenho que acabei de ler e é demais.
And then later, we recorded more 17 minutes with a quality closer to what we call a studio quality recording condition.
Os restaurantes que possuem fogão a lenha estão sempre cheios.
And we also combined both recording conditions as a third experimental set. In the end, we built 4 data configurations to be used in the experiments. The DC1 consisting of all neutral data and only the expressive data of medium quality. And DC2, 3, and 4 consisting of the phonetically rich subset of neutral data and all the possible combinations of the available expressive data. In our experiments, we used the Tacotron-based architecture as our TTS model, together with the style encoder, which is responsible for generating what we call here the latent representation of prosody, or LRP space, which will be responsible for conditionating the expressiveness in the TTS model. And for our audios that we reported, we used the Griffin encoder to convert spectrograms to waveform. And to deal with the multi-speaker modeling, we concatenate a speaker identity embedding into the decoder input. I talk about the style encoder. We tested both the global style tokens and the reference encoder, but both of them were used only to generate this LRP space, which was later analyzed and used to conditionate the TTS model based on the space generated. Additionally, we use the reference encoder as a style encoder together with a classification layer responsible for guiding the LRP space to classify whether the speech is neutral or expressive, adding to the Tacotron-2 loss function across entropy classification loss. And we call this architecture as the style-guided reference encoder, or SGRE. Therefore, at first, we use the DC1 configuration to evaluate how different style encoders model the LRP space, where the SGRE architecture performed the best for us. After that, we evaluated the SGRE architecture in configurations DC2, 3, and 4, evaluating how different recording conditions can affect the model. And as an alternative to subjective evaluation while in intermediate experiments in expressive TTS, we evaluate the space separability between different expressiveness using the area under ROC curve metric of a linear model fitted on top of the style encoder output features, which means that a high ROC metric means that the space is highly separable between different expressiveness. And additionally, we propose a classifier that uses EGMAPS feature extracted from the audios to classify whether the audio is expressive or not, but based on acoustic features related to prosody, where these GMAPS features is a set of acoustic parameters proposed by IB and others, aiming to select the ones that shows a good performance in effective computing tests applied to speech. And it consists of around 88 acoustic features in its extended version that we use it here to make the classifier. And basically, we trained 5-fold random forest on top of the EGMAX features of the training data and use the training model to classify whether the generated artificial speech was expressive or not. And all the metrics were extracted from 150 sentences never seen during the training. And for our results, we used the same visualization, that is a 2D projection using the UMAP method, where the blue data represents the neutral data from the speaker 1, the green points represents the expressive data from the same speaker, and the gray points, the neutral data from the speakers 2 and 3 that don't have expressive data reported. And additionally, we have the centroid of each region and the expressive point farthest from the neutral centroid, used to modulate speech with as much expressiveness as possible. And we call this point the expressive maximum distance point, or EMDP. And after that, to conditionate the TTS model, we used the centroids and the EMDP points. We then evaluated the 3 style encoders and identified that with GST, expressive data is concentrated in the space, but not separated from the neutral ones. And furthermore, it was not possible to generate expressive modulation in speech using this generated space. The reference encoder, on the other hand, generated a more separated space. However, when listening to synthesized audios, it seemed that the model have modeled the recording condition more than the expressiveness itself. And finally, the SGRE generated an LRP space that allowed for a better speech modulation than the reference encoder alone, while still being more separated than the GST. So we choose to keep working with only the SGRE architecture. So then we applied different recording conditions using the SGRE architecture. Starting with DC2, the space seemed separable with a ROC metric of 87. However, when conditionating to EMDP point, the EGMAX classifier only identified 48% of the audios as actually expressive. And the generated audios seemed to model a little of the style, but always with the recording condition of medium quality, as if the recording condition behaved like a strike feature and carried the associated style with it. Using the DC3 configuration, the non-archetypal characteristic of this style seemed not to have been modeled well in terms of space separability, having a lower ROC metric of 81. However, the EGMAX classifier managed to identify almost all synthesized audios as expressive. But however, we do not notice such modulation when listening to such audios. And then, using the DC4 dataset configuration, the LRP space generated by the model looked like a mix of both of the previous ones, and the ROC metric, as a consequence of this space being a mixed representation, have a value of 84, that is between the last 2 experiments. But the EGMAX classifier could identify 87% of the generated audios as expressive, always using the EMDP point. And by listening to the generated audios, we could identify less of the recording condition being modeled, while still modeling part of the style. So now, before showing the generated audios by these last 3 experiments, I'll show examples of neutral and expressive speech, and I will play the ground truth and the Griffin-Ling resynthesized ones. So, for neutral audio,
em Minas Gerais, a temperatura cairá e deve chover à tarde.
With Griffin-Ling.
Em Minas Gerais, a temperatura cairá e deve chover à tarde.
An expressive one.
A gente tem influência em qualquer lugar do bairro. A gente tem influência em qualquer lugar do bairro.
So, just to give a reference to listen to the next audio. So now I'm going to play examples of the generated audios that the model have generated for each data configuration. So like respectively, the results will be played using the neutral centroid, the expressive centroid, and the EMDP point. And they all intelligibly speak the same sentence that we, as Portuguese speakers, we can understand all the words that are being said. So playing for DC2 first, I will play the 3 audios.
Nossas tarifas são as menores da região, confira e verá que somos imbatíveis. Nossas tarifas são as menores da região, confira e verá que somos imbatíveis. Nossas tarifas são as menores da região, confira e verá que somos imbatíveis.
So the expressive centroid was not able to generate a specific modulation in the speech, and the EMDP point can actually modulate the voice, but mostly carrying the recording condition in the background. So now for DC3 configuration.
Nossas tarifas são as menores da região, confira e verá que somos imbatíveis. Nossas tarifas são as menores da região, confira e verá que somos imbatíveis. Nossas tarifas são as menores da região, confira e verá que somos imbatíveis.
So here we couldn't listen to a clear expressive modulation, even in the EMDP point. And finally, using the DC4 data configuration.
Nossas tarifas são as menores da região, confira e verá que somos imbatíveis. Nossas tarifas são as menores da região, confira e verá que somos imbatíveis. Nossas tarifas são as menores da região, confira e verá que somos imbatíveis.
So, with this mixed configuration, we can listen to a modulation of the expressiveness in speech with the EMDP point and with less of the recording condition being modeled. And for all the experiments, the expressive centroid was not useful to control the expressiveness itself. So, for our experiments, we verified that the style encoders do allow a speech modulation easily. However, when working with non-archetypal styles, it seems that the model tends to generate an LRP space more associated with the most striking feature, be it like recording condition or the style's prosody. And the guided architecture and different data configurations seem to help to a better modulation of the expressive speech. And we also proposed a preliminary evaluation for intermediate results using the area under the ROC curve to measure the separability of this space and the EGMAPS classifier to identify expressiveness in the generated speech using specific prosody parameters. So thank you for your attention.
Hello. In fact, I always distinguish between emotional content with attitudinal content. Here you are addressing some more attitudinal content where the prosody should be aware of the linguistic constituents. You know, it's like sarcasm. Sarcastic speech is somehow should be aware to what word carries sarcasm. If you say, I'm intelligent, you are intelligent. So intelligent is a focus of this attitude. And it's the same for what you are addressing. Enthusiastic, you are enthusiastic. So this entanglement between text encoder and prosodic encoder doesn't hold, in my opinion, for attitudes. Because the prosodic encoder should be aware of the linguistic constituent, so that to insist, for example, to specific words. So perhaps, in my opinion, this strong separation
where the prosodic encoder is not aware of the constituent, the words. It's sometimes it could make some problems of for the modeling. What is your opinion?
Well, like this was an experimental paper, yeah. Like we were trying the different time encoders that were reported in emotional speech, but I agree with you, like in our later results, we think also that trying to model like word related or like phonetic related prosody instead of like the sentence, a global way of modeling it could help. Specifically because of that, because like it is a social attitude style and not like an emotional one that can be perceived like as a global dependence.
Okay, thanks. Please.
Hello, thank you for the talk. I have a question. If you know beforehand which style the speech is in, why don't you use some sort of a shifted prior or not provide this information in order to separate the space?
Did you mean like using the like the label of the data to condition age, like priorly in the architecture? Is it?
So you can either use it as an explicit label, or you can use it as a, you know, as information to shift a prior, which you use, for example, in variational autoencoder.
Oh yeah. Like we plan to test actually different architectures, like with the hypothesis that it's not only data that can extract these features, but also the prior in the architecture can do this. And like using VAI structure after the reference encoder could help with it. Some papers have already showed it in some results. And like in this specific project, we just wanted to see how well these architectures with no change at all, only for the SGRE architecture that we tried to modulate it better, to see how these architectures work with our data. And with the hypothesis that we can make little changes in the architecture to deal better with the prosodic modeling. And for sure, like adding priors in the architecture is our future plans to do with this problem.
Thank you.
Thank you. This is not a question, but this is a remark, or maybe it is a question. I don't know how Brazilian Portuguese and native Portuguese is different from each other. What do you think that these methods would give the same results for native Portuguese as well?
Oh, I think like for native Portuguese, like from Portugal, I think the languages are very different. So the architecture itself should work, yeah, for like it's not language dependent, but maybe the perceiveness of the people listening to such audios could be different, because like inside Brazil, we have a lot of different accents depending on the region, because it's a continental country. And when we compare it to like Portugal Portuguese, it is very, very different. So I cannot have a conclusion about it, but since they are very different accents, actually, I think the perceiveness of the people listening to such audios would be different. As the enthusiastic style for Brazil would be not the same as the enthusiastic style for Portugal speakers.
we were in Portugal. This is a remark, my remark, in the late 80s, because in the late 80s, we developed the first Portugal text-to-speech system in Porto, the Porto University. So I am very close to Portugal researchers. Thank you very much for your nice presentation.
Thank you.
Now, ladies and gentlemen, this was the last talk for today, and I can summarize that this topic, expressive speech synthesis, is a never-ending research area. I mean, the next decades, we will hear a lot of talks about these problems, because this cannot be exactly determined by data, like human soul. Thank you very much, and I give the talk to Géza.
Thank you. Congratulations to the audience. We have a long day, and we still have some time to go together. So one possibility is for the online part, maybe our technical people can have how we can move to spatial chat for discussion for having all the others. But for those who are here, I recommend just to have a short introduction, because it's much harder to ask everyone one by one with these relatively small name tags. So it's not a very big group. And we have time until 6, I think, that our welcome reception will start then. So I think it's enough for like everybody introducing themselves. But well, I did the introduction about myself, so there is no sense of doing that. So maybe in some order we can try. I don't want to force anybody, but maybe just in the order we are sitting, like we could start maybe from here, if you don't mind, and then go around. So Gábor already introduced himself, so he had an option if he wants to come in the end. So maybe just those who are in the front, you can start, and let's use this opportunity, because well, we'll be together like in the next 2 days as well. So let's use the opportunity that everybody knows everybody. It's not a very big group, so we have time for that.
Should I just go?
Yes, you should go.
Oh, there.
Because of the camera.
Hi, everyone. It's nice to meet you. My name is Oriane Sharoni. I'm from Israel, and I'm here as part of UpAI. It's a consultancy and a startup that works a lot with audio. And this day was fascinating. So thank you for all the speakers.
Hi, I'm Roy Schanberg. I'm Oriane's partner at UpAI. Thanks for this wonderful day. We do a lot of work with audio, and we're interested in seeing the state of the art, and it was very interesting to see it here. Thank you all.
Hello, my name is Olivier Perrotin. I'm a CNRS researcher at Gypsy Lab in Grenoble, France. And my main interest is expressive speech synthesis, and mainly in interaction. So like how can interact with a synthesizer that is talking to us, or how we can speak with the synthesizer instead of our own voice, and then how to interact with it to convey all the expression we want the synthesizer to speak with.
Which language? French and English.
Hi, my name is Grant Reber. I work at a startup based in Kiev called Respeecher, and we focus exclusively on voice conversion. And our customers are people who like the movie and video game industry who use it.
Hi, everyone. I'm Tamás, Csapó. I'm a postdoc at the Budapest University of Technology and Economics. And during my PhD, I was mostly focusing on vocoding and excitation models for agent-based speech synthesis. And after that, as you could see in the presentation, I'm mostly interested in articulation and ultrasound and like that.
Hello, my name is Csaba Zainko. I work at the Technical University of Budapest here, Hungary. I deal with deep learning, speech synthesis, human-computer interaction, human-robot interaction. That's all.
So Gérard, I'm a PhD student at Gypsalab. So yes, I am interested in fact in the moving forward from text-to-speech system to conversational systems, of course, to use this technology to interact with computers which have intentions of communications. And not only, mediating, in fact, text. In fact, I have two questions which really interest me, which is not very well treated for now. The first one is how to say use technology for data mining. So we can process large corpora now. But it doesn't benefit to linguistics or phonology or phonetics. We compute a lot of embeddings, prosodic embeddings, wave-to-vec, art-to-vec, and so on. But nobody really explored this representation, this Latin representation, to try to understand if we have missed something in phonetics or in phonology. So perhaps a way to balance or to bridge between technology and science. We are doing too much technology for now, compiling some networks and so on. And I forgot about the second one. Okay, so try to process the first one. It could be interesting. So guys.
Well, you already saw me before. I'm Esther Klauwers. I work at ReadSpeaker. It's a small text-to-speech company. I'm also on the board of SynSig, the special interest group for speech synthesis. And my interest is in prosody analysis and modeling for synthesis, and being able to use linguistic and prosodic knowledge to improve the synthesis and make it more available and more appropriate for use in different types of applications, such as dialogues and games and what have you. So, thanks.
Hi, everyone. My name is Fat Rowe. I'm a second-year PhD student at the University of Groningen.
I work mainly in speech synthesis for under-resourced languages. I'm based in Friesland in the north of the Netherlands, so I'm also working on the local language depth region. This is actually the first academic event that I attend in person, like ever. So, and it's been amazing so far, meeting everyone here who more or less shares the same interest in speech synthesis. I'm looking forward to the next few days. So nice to see everyone.
Hello, everyone. I'm Bence Halpern, a final year PhD student at the University of Amsterdam. My main research interest is pathological speech synthesis, but I'm interested about evaluating speech signals in general, naturalness of speech signals, and objective speech evaluation too. Yeah, thank you.
Good evening, everyone. My name is Adeze Edigwe, and I'm a first-year PhD student at Wheat Speaker, a company in the Netherlands, and Esther is my PhD advisor. And I'm also a PhD student at University of Helsinki as part of the Conversational Brains EU project. My research is on conversational speech synthesis, and part of my lines of research is exploring how we can build and collect better conversational speech data to train our models on. And a second one is to build context-aware TTS systems. And so how can we synthesize speech that is more appropriate to the preceding response that you see in dialogue systems, so more meaningful prosody. Thank you, and I'm looking forward to meeting everyone.
Good evening. I'm Martin Longley. I'm working in the JIT lab with Olivier and Gérard that you just saw, that you just met. Apart from the work that I presented this morning, I'm actually working on understanding what is encoded in the embeddings that are outputted by the encoder of a text-to-speech model that we use pretty much every day. Understanding what is encoded in these embeddings, and in particular prosodic and acoustic aspects as duration or form and frequency, for example. And I am also interested in how to evaluate the system, because I think that those the methods that are used now are not enough for the standard quality that we have achieved with text-to-speech model. So this will be one of my particular issues. Thanks.
Hi all, my name is Vyacheslav Plinkov, for short Slava. I'm applied scientist in Amazon in text-to-speech research. So I work on different components of neural text-to-speech. So pretty much any peculiar research on speech synthesis would be of interest for me. Thanks.
Thank you. In the meantime, I saw that Peter wrote it in the chat, that those people who are online with us, they are also encouraged to introduce themselves. So if they raise their virtual hand, then they can elevate to anyone to be a panelist and to be able to talk. So I asked Peter just to tell me if somebody showed up.
Until we didn't see any people to raise their hands. If we see any, then we will elevate them as a panelist.
Okay, so I'm quite happy to see that a number of people mentioned context. because that is also has been my interest for a long time, but we couldn't put it together in a realistic project-like thing. So, for example, to cover sarcasm, as Gérard mentioned, actually you have to have a very high level of understanding. So it would be like also to have a virtual brain as well. Yes, French. Yeah, they might be some people. Yes, some French people are by default they have sarcasm, so it's easier. But so I like that there is this interest, and I encourage everyone to talk and to think about of what kind of context can be realistically taken into account, what sort of data can be done, and maybe what could be like today or in a short time a realistic scenario when that can be applied.
There is Vivian who just became panelist, and it means that he might be able to switch on the microphone and he can introduce himself. Vivian?
Hi, we're Vivian, Tian, and Alexandra. We weren't able to attend in person, but we've been attending together in London. Hello. We're at Paper Cup, by the way, small startup interested in TTS.
Was very quick, so I just couldn't catch anything from that. So maybe, yeah, I speak Hunglish, so maybe you have to slow down a little bit and explain it more.
And sorry, we said we're Vivian, Tian, and Alexandra, and we are sad that we weren't able to attend in person, but the three of us are watching from London, and we're from a startup called Paper Cup.
Okay, thank you. With that addition.
They can introduce themselves.
Can you show themselves like one by one, if you turn on your camera? And yeah, I see there's 3 persons, but we would be happy to know your name at least, so that we are a small group now. So why not like know the names? Just sure. when you raise your hand, just tell your name at least, and also maybe your interest.
I'm Tian. I did a master's in machine learning and now work in speech. Interest in end-to-end TTS, both in expressive TTS as well as kind of scaling TTS to many languages.
I'm Alexandra, did a master's in speech and language processing, and am particularly interested in linguistic applications to TTS.
I'm Vivian. I did the same master's as Alexandra in speech and language processing. Similarly interested in end-to-end TTS, cross-lingual, and low-resource TTS.
Any questions from the audience who are here to this very nice group, who were brave enough also to be the first who joined in remotely? And I hope that you will join in tomorrow and the day after tomorrow as well. So from here. So, for example, will you tell us something about the scenario on which you work? So it's probably you imagine something where you would use your cross-lingual text-to-speech.
Sorry, so we work at a startup called Paper Cup, and what Paper Cup does is, I guess you could say, machine dubbing. We essentially translate content, video content primarily, from English into other languages. And our machine learning team focuses primarily on the TTS aspect of that, so the final part of the pipeline. And so we translate into several languages now: Spanish, Brazilian Portuguese, French, German, Italian, and am I missing one? No, is that it? Okay. Yeah. So that's our use case.
So I encourage you to cover all the 7,000 languages we have.
Yes,
so
that's the dream.
Okay, any more questions from here or anyone else raising their hands?
Just to mention, perhaps.
No, come please.
Hi. Just for a few days, I'm still on board of ISCA. You know, perhaps that there is a new special interest group on spoken language translation. So they want to do end-to-end translation of one language to another. So it could be interesting for you, in fact, to have a look at this special interest group, because there are some bridges between the different things. Spoken translation, of course, includes spoken generation of speech, but also this problem of how to map prosody, for example. Sarcasm is not implemented the same way in French or in Hungarian, or not implemented at all in Japanese. So it's interesting for you, for your group to be in contact with this new SLT special interest group.
So what is it called? SLT?
Language translation.
Okay.
It's headed by Satoshi Nakamura in Japan. So it's interesting for you, at least to have a look. And so you can bridge between the two SIGs.
Sounds good.
Thank you.
Thank you so much.
But at the same time, don't forget about SynSig, because the conference is for SynSig. And yeah, we are happy to share, and we are looking for wider contacts, even if now we are limited in travels. So one more call to all the others who are online. Is there anyone? Not yet. So then we have a welcome reception at 6 p.m. at this level, but the other end of the corridor. So until then, we can just chat locally, or if you want, you can go to the spatial chat window. If there are people there, then you can use like the virtual chat infrastructure. So 6 o'clock at the end of the corridor. As I see, there is some rain, so it's better to be inside than outside, and also we can have some nice time together before we go to bed. Yeah. Okay, that's it.